Hello everyone, my name is Andrew Laban and I'm here with my fellow Team 68 engineering members Nihar Mehta, Aroni Baduri, and Jason Scott to present to you the proposed design for our hydro pump storage system. For decades, scientists and engineers have searched for new ways to retain renewable forms of energy. One groundbreaking type that has been developed is acquiring solar energy from the sun. 430 quintillion joules of energy from the sun hit the Earth every hour, and obtaining just a fraction of that energy is immensely valuable for us as humans. However, since the sun is only available during the day and not at night, this poses a few problems. What happens when there is demand for energy during the night? Or what happens when there is no energy during the day? These questions bring us to our proposed solution. We need a method of storing this large amount of solar energy so that it can be managed and distributed when needed accordingly. There are many different types of solar energy storage systems currently in use. At the Power Reserve in Hornsdale, Australia, there is a battery-based system that can store up to 129 megawatt hours of electrical energy. Additionally, there are vacuum-sealed flywheels in use which operate by accelerating a rotor up to 50,000 revolutions per minute. This method uses rotational energy as storage. For this project, however, we have been hired by Seymour Crystals Incorporated to design a mathematical model for a hydro pump storage system as a method for storing this excess solar energy from a designated solar field. The system was to be efficient, low cost for installation and operation, and ethically sound. It was decided to consist of two main processes. The first process will incorporate a pump system where water is pulled from a river and pumped up a hill via pipe, and then stored at a higher elevation than it was initially. This pumping system converts the solar energy from the sun to kinetic energy by giving the water a velocity. The water is also being moved upward so it gains gravitational potential energy, which is ultimately the form of energy by which it is stored. This system uses water as the mass that is consisted of by the kinetic and potential energies, hence the description hydro pump storage system. In a practical scenario, any excess solar energy from a solar field will power this pump system to store it in the form of gravitational potential energy. Then, when there is energy needed by the system, it will take this potential energy and convert it back to usable energy, which brings us to phase 2 of the hydro system, the turbine system. When prompted, the stored water at the top of the hill will be released down one or multiple pipes, converting the once potential energy back to kinetic energy. The kinetic water then flows through the implemented turbine and outputs electrical energy, which can then be used for whatever it is to be desired. In order to design this hydro pump storage system, we were asked to create a mathematical model that would account for any potential relevant changes in energy this system may experience. We decided to utilize a Python program to obtain the best possible combination of design implementations and yield the most efficient, low-cost system. Researching various information about existing hydro pump specifications and possible piping configurations also would be necessary to best optimize the system. In addition to these technical project requirements, we were asked to keep track of our progress via an electronic design notebook and to complete a full report on the project. To keep track of all these goals and ensure we achieved all of them within our allotted time frame, we decided to assign each other primary positions. Nihar and Aroni were in charge of developing the Python program, while me and Jason were responsible for any necessary research. Additionally, Nihar and I were tasked with creating the model for the design, and Jason and Aroni were in charge for the documentation and the overall design of the project, respectively. Another big part of our project management was outlining all of the tasks we needed to complete. We decided to organize the main jobs to be completed in a work breakdown structure, which will be found in our final notebook for this project. The work breakdown structure served as a crucial reference source for ensuring the completion of all required tasks. We also decided that choosing a specific timeline for each task in something like a Gantt chart would not be necessary for this project because of its short 2-week time frame. As a team, we quickly concluded that creating such a chart would take too much time for what it would be worth, so we stuck to a work breakdown structure.
The first major decision in the design process of this project we had to make was choosing where it would be constructed. For this, we had 3 options, so we created a decision matrix to help to identify the best location. The factors we considered were the usable space, elevation angle, horizontal and vertical distances from the zone to the river, additional cost, and other notable features, ethics. In our design matrix, we had to keep in mind ethics, cost, and efficiency, as those were the main priorities specified by Seymour Crystals Incorporated. Zone 2 was quickly eliminated based on 3 main factors. First, this zone was a horizontal distance of 130 meters away from the river, meaning more work would be required to move the water up to the high-level reservoir. The second factor against Zone 2 was its estimated site preparation cost, which was 50 cents per square meter. This was 100% and 67% more expensive per square meter than Zone 1 and 3 respectively. Lastly, Zone 2 was likely an ancestral burial site, according to the local indigenous people. We valued ethics highly in our decision matrix, so that reflected on Zone 2's score very poorly. Any positives of Zone 2 were strongly outweighed by these described detriments. The decision between Zone 1 and Zone 3 came down to cost and complications. Zone 3 had a circular reservoir, and its pipe configuration consisted of 2 bends. Additional complications included a large area of trees that would need to be cleared, and a very far access road which would cost roughly $150,000 to install. While Zone 1 also had complications involving possible chemical agents in the neighboring soil, this only amounted to an extra $10,000 initial cost. With all of that taken into account, we settled on Zone 1 as our location of choice. Choosing the location of the proposed design, the next step in the design of this project was to establish which factors were significant in affecting the energy yield of the system. For this design, the design output given by our customers was 120 megawatt hours. In a perfect situation, our input energy would also be 120 megawatt hours, assuming no energy losses in the system. However, there will inevitably be energy consumed by the system for several reasons. 2 of these factors are directly related to the efficiencies of the pump and turbine. Because these 2 mechanisms are not perfectly efficient, there will be energy loss likely due to heat, sound, and vibration. Additionally, there will be a bend in the pipe that will deliver the water, causing a loss of speed when the water passes through it, thus decreasing its kinetic energy. Lastly, we had to account for the friction the water would experience passing through the pipes. Since there is contact between the pipe and the water, there will be some energy loss due to friction. In order to account for these energy losses and represent them in a comprehensible way, we decided to use the universal accounting equation. The potential areas for energy loss can be expressed by these equations, and we will go more in depth explaining them in our final project report. Some of these variables were predetermined due to the site we chose, while others were design choices. It was our job to figure out the best combination of variable variables that yielded the highest overall efficiency and the lowest overall cost, including installation and operation. There are a number of assumptions we had to make for this design in order to simplify it to some degree. These included the following. The efficiency for our model is exactly what was calculated. There are no air gaps in the pipes when water flows through them. There is no loss of water from the reservoir to the end of the system, and the water that flows through the pipes has mostly laminar flow properties compared to a rather turbulent system. A laminar flow is when each layer of water molecules all flow in the same direction, with each layer moving smoothly past the adjacent layers with little to no mixing. The water in the pipes will not have a perfect laminar flow, but we expect them to have little turbulence when flowing through the pipe. Additional numeric assumptions related to the accounting equation are the magnitude of acceleration due to gravity, which is 9.8 meters per second squared. The density of water is 1,000 kilograms per meter cubed, and there is no initial or final energy in the system.
There is a potential for energy loss when the sun or weather heats up the water. When hot water is being transported through a pipe, it can create something called flow-accelerated corrosion. In this process, the increased velocity of water in pipes begins to dissolve certain materials in the pipe. This corrosion can become aggressive if the water is hot and persistent enough and will cause leaks in the pipes. Furthermore, this will essentially cause a loss in water and overall energy, effectively reducing the efficiency of the entire system substantially. Another potential source of energy loss can come from the pipes being kept at too low of temperatures. If pipes are kept at sub-zero temperatures, the water inside of them can freeze. This can cause the pipes to expand and rupture, which would then additionally cause the entire system to fail, since water would not be able to flow from the river to the reservoir and back to the river. This should not be a problem for this model because it will be in a moderate climate where the temperature will never reach below zero. Some notable variables we decided upon based on many decision matrices and our Python program are the pump efficiency, turbine efficiency, pipe diameter, and reservoir depth. Our pump and turbine efficiencies were chosen to be 0.92 and 0.94 respectively, which were their highest potential values. The premium we paid for the maximum efficiencies was possible by saving draining time and money in other areas of the system. We went a little more conservative on the pipe diameter, going with 1.75 meters. This pipe gave the water enough time to empty within the 12-hour allotted time frame, while also not cutting too much into our budget. Lastly, the depth of the reservoir was decided to be 10 meters. We wanted to keep this value as small as possible because the walls to surround the reservoir were very expensive, and we preferred to increase our tank volume by increasing the area of it instead, since that was cheaper. This brings us to our final values relating to the outputs. The final area of the reservoir measured out to be 142,000 square meters, which fit well within our 360,000 square meter constraint, while minimizing the site preparation costs. The total cost of the operation ended up being $514,203, which was actually 14.3% less than our initial upper target bound cost. Lastly, the overall efficiency of our model was 0.7813, meaning there would need to be a solar energy input of 153.6 megawatt hours to produce the needed output of 120 megawatt hours. Lastly, the time to fill and time to drain were similar at 11.92 hours and 11.24 hours respectively. This 11.24-hour empty time leaves just under 46 minutes of leeway for the 12-hour limit. Now, Nihar will explain how the Python program helped us figure out the most optimal values.
The code we developed to represent our model consisted of 5 main sections and followed a similar layout to the sample inputs and outputs given to validate our model. The first step was to declare the assumed constants, which can be seen at the top. Next, we set up the input statements needed to account for all the design choices we had to test out. This was a fairly simple process, but one of the inputs that needed a bit more than just simple statements was the input for the bend coefficients. We tried to base our model on the idea that we could try many different combinations, which included changing the number of bends. So we used an array and a loop to get the inputs of as many bends as we wanted to test. After the inputs came the 2 sections responsible for doing all the calculations of the model. The intermediate calculations involved relatively simple equations, but the math calculation was a bit more complicated, since it involved one of the 2 universal accounting equations for the model. This equation established a relationship between numerous components for when the water is flowing down to the turbine that allowed us to solve for the mass with the known values we had so far. After these calculations, we had the main calculations that would get us the outputs we needed in order to optimize our design the best we could. The second universal accounting equation of the model would be used in this section to solve for the input energy needed to get the specified 120 megawatt hours of energy as output. The final section was the outputs, and this was the simplest section since all we had to do was print out the values we needed. To demonstrate the functionality of this model, I have pre-programmed a set of values that yielded poor results, as well as the values of our final design into the console. When we run the code, we get the 5 main outputs that would help us finalize our cost and determine the overall effectiveness of our design. As seen in the outputs for the poor set of values, the efficiency was extremely low at just 21%, while the time to empty was also too high. In the output for the final values we choose, we can see that the efficiency is pretty high at 78%, while the time is also under 12 hours. Similar to this comparison, we executed this model numerous times with specific combinations and also iterated some specific variables to see the different results and the effects of the specific variables. Through the use of design matrices and interactions through this model, we were able to reach our final values that yielded a good design.
We believe that this is the best model available for the hydro pump storage system, considering its few shortcomings and the fact that it will be the most cost-efficient going forward. With that, we have concluded our presentation. Thank you to Seymour Crystals Incorporated for the opportunity to present a potential model, and thank you for listening.